All right. All right, now I'll start recording. Okay, the- there is a new assignment out. Sorry, 5700. I will copy it over to you shortly, but it's exercises out of chapter 2. Also, I will get you a review sheet. We need to be looking into another exam before the drop date. So that's probably, do both these on the same day. I think I'll put yours out to, last day to drop is the 29th. I will arrange stuff. So we'll aim for an exam on the 27th. And particularly if you are feel like you're in a critical situation, let me know and I'll make sure that you have your grades and your totals and everything so you know where you stand. All right. And that new homework is due in a week. I wanted to review, just go over PDA example. And then somewhere, okay, back around page 115, we put on the board the processing that went on for doing the A to the N, B to the N. And it was similar to the example on page 115. I wanted to, yes. No, it'll just be on what we've done in this section. So let's see. I'll give you the review sheet and everything, but I don't think, I mean, there's some big ideas like the languages, big set of context-free languages, but not intended to be particularly cumulative. So stuff from the last exam, you're not going to see, other than if I warn you. So the basic layout for that. Let's see here. Either heavy breathing or lost the meeting. Here we go. remember the PDA is a state machine similar to the DFA and NFA that we've seen. It is non-deterministic, and it has a stack. Non-deterministic. Okay. And so we also said for trying to come up with a practical way of using it, there's no like, we don't have if statements or means of telling exactly. There's no logic that says the stack is now empty or the stack is not empty. So what we do is the trick for the examples that are in your book is that we push a $sign on just something that we can recognize as here's the bottom of the stack, and we need to get back to that before the typical pattern is, right, on an epsilon move, if there's a $sign there, pop it off, and you can get to the accept state. So the machine itself, trying to not make it too confusing here, the machine will accept. So I guess the internal circuitry of our imaginary machine is such that it knows when it's in an accept state, it knows that the stack is empty, and it knows that the input is used up. So all three of those conditions have to be true for it to actually say, yes, I accept this string. Right? Makes sense. It must use up all the input. I think one of the questions on the exam was, an NFA can accept even if some characters are left over at the end. Few of you fell for that. But you can't just have extra characters and accept, right? You have to find a path to the accept state, use up the input, and NFA is happy with that. PDA needs also you cleared out the stack. So in order to support that, just as a simplifying way to use the stack, on an empty move, the first thing we do, we don't care what's on the stack, and we push on replace anything. We just add the $sign onto the empty stack. Then, if we're doing, your book uses 0 to the n, 1 to the n. I did in class. Like this. And so we went through, I just wanted to trace one through, think about the essential strategy of recognizing whether a string is in the language or not is, and the strategy is to push something onto the stack every time you see the first set of characters, and then to pop those back off when you see the second desired set of characters. The only way, if you do it right, the only way it can be happy and match up is if there were an equal number of the first character and equal number of the second character. And what it should do is fail in any other configuration. So we want it to succeed only right? So it should fail on for example, it should fail on these clearly not client strings. And probably the most uncomfortable thing about it is the idea that it's non-deterministic, so it's going to try every possibility along the way that it could do with the legal moves that it has. And we're going to note that when it ends up with nothing that it can do, then it stops and it fails. Yeah, because if there's nothing it can do, that means there's still input left. It doesn't have a transition. So what we said was, remembering this is the format is the first thing before the comma is this is the character that I see in the input and I'm going to consume it. And then the second after the comma is if this is on top of the stack, replace it with this and take this transition. So using the empty string always succeeds. So when you turn it on, it would spontaneously put the $sign on the stack and move to Q1. And then Q1 is going to try, and it's going to say, if I see the letter A, and I, just to kind of expand the example a little bit, I let it, instead of just pushing the A on, I said push, say, a capital A on the stack. I could push a W or a ampersand or any little happy character I want to put on there. But I'm actually going to segue into how can I translate a CFG into a PDA? So I'm prepping you for that. So every time I see an A, I'm going to push a capital A on the stack. And then what if I finally see a B? If I see a B, it's going to move me to let's look for B's. And there's an A on top of the stack, pop it off. So in order to take that transition, I need those two things to be true. And I'm going to loop, repeating that same thing, like so. So if we take the accept path first, okay, so that fills in the machine. You should, I'll say it again, you can reference page 115. And I'm just trying to show a little bit of variation from the one example he has here. What we're doing is he pushes zeros, set of zeros on for every zero he sees. And then when I see a 1, I start popping off the zeros that were on the stack. And ideally, the only way I can get to, in this case, we're pushing A's and popping them back off when we see B's. And ideally, if this works correctly, the only way I can get to Q3 is if I have starting with N A's and immediately following that with N B's, and that's the whole input string. Otherwise, it should get to a point where it can't advance and can't get to the accept state. So I don't know. Let's try the. What if I feed it AAB? So if we trace what's going on, we start in Q0. Immediately, without consuming any input, empty string, I push the $sign on of the stack. And that gets me to Q1. I'm now, the input is still at the front. I see an A, and this tells me push a capital A onto the stack and consume that input. So that uses up the first A and brings me back to Q1, and I'm now looking at the next A. It's not a B, it is an A, so I'm going to follow that route and push the second A on there. And it advances the input, so I'm looking at the B. I'm in Q1, I have a B, and lo and behold, there's an A on top of the stack. So this says pop it off and move to Q2. Okay, Q2 says, well, hey, I can jump over to Q3 if I don't use up an input and there's a dollar sign, which is neither of which is true. Or I'm sorry, it would not try to use any input, but it doesn't have a dollar sign to try and move. But it's looking at a B. Oops. The B got us down to here. And now we've used up the input. I can't do this transition. There's not a dollar sign to let me go to that transition to Q3. And so there's nothing I can do. In this case, I used up the input. I'm not in an accept state, and the stack is not empty. So that would give a non-accept or a fail. Making sense?
So the epsilon transition down there.
Yeah, thank you.
That that can only be traversed if the dollar sign is on top of the stack. Okay? So
yeah.
Unlike previous situations where if you had an epsilon transition, it would automatically make
Yes.
all those states. This will only have the,
yes.
the stack conditions, right?
Yep. Yep. You have to have the stack and the input symbol match.
Okay.
So if we were to implement this, would we I think that we would need to pop from the stack first and check if.
Well, what you might actually have to do is do a check. You know, your stack operation would probably need like a peek that tells me what is on top of the stack without necessarily pulling it off. It's kind of the cheat way to do it. Otherwise, yeah. So you could look. In order to do this, it has to know what's top symbol. And if the top symbol doesn't match, then it has to sit there and look for another alternative.
If you pop it.
Well, you could pop it and then look at it and then push it back on if it's not the right one. I mean, right? You'd have to do something to not alter. You don't want to alter the stack if you can't take that move. All right, so that was the first fail using this one. What if we feed it the BAAB? It's going to fail faster with the this one BAAB. It's not going to get very far at all. It's going to immediately put the dollar sign on, and if it sees an A, it would push an A on. Right now it sees a B, but there's no A on top of the stack. So that transition can't take place. So we're stuck in Q1. We've got input. The stack's not even empty. And there's just no moves that we can make. There's nothing that matches. So it would have to just shut down and say fail, which makes sense, right? That certainly is not in A to the N, B to the N. It's starting with a B, and so can't go any further. So those are two fail modes. First one, we couldn't get the rest of the stuff popped off the stack because there weren't enough Bs. And this one, we can't even get out of Q1 because we haven't met the condition. So you can kind of see there's kind of a cleverness the way this works, right? Because we said this is the only thing that should work. So we want to make sure that our operation of this machine is going to not be able to push on and try to keep going if the string is not in the language. And then our happy path, we start with nothing. This one, two different markers. So immediately we push the $sign on, and we'd be looking at that first A. So we can take this is the only option we have. We should push the A on and advance us. We take that loop again, pushing the A, capital A on, and advancing. And we do that yet one more time, and A, and we don't care, push an A on there. Now that advanced me to looking at a B. There's no looping around here that would do on a B, but hey, if I've got an A on top, I do. I've got a B here, I do. And I can take this trip down to Q2, popping this A off and advancing my input. Now I'm in Q2, and I see this B. I'm going to pop off the A, advance the input when I take that transition. I can do that one more time. Got a B, A, go through. Now I'm recognize I'm at the end of my input. I'm in Q2, and now and even if I were not at the end of the input, let's just quickly, if I had an extra B hanging off over here, I could attempt this move to Q3, but I've still got extra input, so that would end up in a fail. But on the happy path, where I do have a string that's in the language, I take that last one here, popping off the A, and now I've got, without consuming any input, good, I don't have any left. I can $sign gets popped off, and I can do this transition where all three conditions are met: the empty stack, used up input, accept state. And that gets me there. Right, so does that make some sense? Yeah. Okay, so you should be able to, a good exam question would involve either, giving, we've kind of beat this one a bit, but certainly should be able, given a machine like that or similar, to trace through, would these strings be accepted? Which of these strings would this accept? Would this machine accept, say, or something like that? Given the transitions and the machine, without necessarily either given, what it is supposed to accept, or possibly you've got to figure out, just without knowing what the definition of the language is, is this string accepted or rejected by this particular machine? Okay, so doing a trace. So you need to know how the PDA would process. the, let's see, I think this is, let me double check. We will not spend time on the non-context free languages. I think heading into our exam, double checking. Yeah, we're pretty much heading into the last of the material that will be part of the exam. So I will, see, how many of you have had me before? Okay, so you know we'll get to a review sheet a week before the exam, and the exam will come off of the review sheet. So your best strategy approach to that would be make sure that you know how to do the stuff that the review sheet says. Make sure you can do this. What's the difference between this? You know, have that stuff down, and the questions on the exam should be familiar and at least no surprises for those who take steps not to be surprised. We talk about the sympathy curve. Sympathy curve is a very important part of the class. So sympathy and responsiveness to questions starts out really high. This is my teacher sympathy.
This is something that's part of the class.
This is something that you should be aware of. I will not test over it directly, but see, we have this kind of asymptotic activity going on, such that it gets really small, infinitesimally small. So ask questions early and prepare. For example, I gave, what's that?
For example.
Now, for example, if you come to me the night before and say, could you tell me how to do problem number 3 on homework number 1? Then sympathy, depending on the mood. This is very mood dependent, yours and mine. It's gonna be kind of small. If you ask me a question, you know, even a day before it's due, then I'm much more sympathetic. I still, an hour before, then that's gonna be down here. And I will purposely try to mislead you. Oops, delete that from the record, please. No, I will not try to mislead you.
You might just not respond.
I may not respond. Yeah. So, for example, I had a say, no, not automata. Never knew of those. You guys are beyond that. It was actually a data structures student who came up to me after the exam and said, wow, that seemed really hard for a 100 level or 1000 level exam, 1140. I said, really? People usually do well on exam number 1. I said, did you spend some time with a review sheet? He said, well, yeah, I kind of went through most of it. I said, well, I gave you an example exam. How hard was that for you? Did you get, well, I didn't really have time to go over it. I said, oh. Yeah, then I suppose the exam would seem pretty hard if you were totally unprepared for it. You can lead a student to knowledge, but you cannot make them think. Play off of the old horse, water, drink thing. You have to explain it in graphic. Okay, so let me leave this a moment. So here is what people usually find when you look at something like this, you go, well, yeah, if you kind of happen to see the trick, you can kind of get, okay, I want to match the number of these, the number of that. I guess I push them onto a stack and pop them back off. That kind of follows. But what about any kind of grammar in general? If I've got a CFG, I know that there exists a PDA that will accept it, that will tell me whether I can construct a PDA by definition. And see, actually, there's a theorem to that effect. Equivalence with context-free grammar is page 117. A language is context-free if and only if some push-down automaton recognizes it. Is a regular language a context-free language? The answer is, well, sure, right? Remember the little diagram? It says the regular languages are just a subset. So they are, in fact, also context-free. Any context-free language can be represented by CFG, and that also includes any regular languages also could be accepted by CFG. So can we convince ourselves, how would you build a PDA? So here's where we're kind of, we see the PDA, and we would like to know, well, can I use a PDA to accept a regular language?
Oh, yeah.
This time I'm not leading you down a deceptive path. But I could. Watch.
Just also,
So sure, because it is also context free. So, how would I do that? So if I've got, here's a nice little, let's see. Something that's not too boring. So hopefully at this point you can recognize what this guy looks like.
Yeah.
It's a series of ones ending in a single zero. So this is like, so this is the this is a DFA. A regular expression would be what? Yes. How about any number including 0 ones followed by a 0? Okay. Could I make a PDA to do that? Ought to, right? Ought to be able to. Get from the question of,
You can make it.
could someone somewhere make a PDA versus can you make a PDA that looks at that, right? Well, what's a PDA?
That's it.
Kind of a DFA with a stack. Do I need to use the stack?
Has to
I
be empty.
can
That's-
leave the stack empty, right? PDA, let's just do, I don't know, Q0 on a 1. Don't do nothing with the stack. That was bad English on purpose. Yeah, I don't think I used it here. English in my Deep Dark Secrets box is the fact that I obtained by legal means an English BA. That's the first thing I did. Which opened up doors for
Nothing.
no. I laid carpet. You need fix it bigger man than I to lay carpet. Literally, I mean, like, you need to be kind of heavier duty. Larger, heavier, so that you can kick in the carpet without breaking your knees as fast. It opened up doors to sell stereo equipment. Problem was, I was kind of had some teacher qualities built in, and so I would teach the customers all about stereo equipment and which were the best buys and which were the best stats and, you know, specs to look for. And then they'd go over to the other stereo store and save, you know, $5 on the sale and get something. Whereas the manager, salesperson, could sell the literal sell ice cubes to Eskimos kind of person. People walk, it didn't matter. You go to the manager, old Bill could sell anything. People walk out like, they didn't even want something when they came in the store. They'd walk out and go, all right, this is the greatest deal in the world. So I did not have that capability. Anyway, so I like to, I was going to teach English, so this all is the segue into my English professor joke. English professor says, don't stop me if you've heard this before, because with all that build up, it would only break my heart. English professor says, in the English language, in a very boring word, two negatives make a positive, but two positives can never make a negative. From the back of the room, he hears, yeah, right. Okay, well then, what we want to do is make the PDA. So the PDA just doesn't do anything with the stack. So it's really easy to convert a DFA to a PDA just by who cares about the stack? We don't. We just do. We just add stack moves onto the transitions that don't do anything, right? So we're happy with that. Same old thing, right? So here's a PDA. We just add this. We don't do anything with the stack, and it perfectly is happy to.
But can a PDA go to zero null states?
Sure. There's nothing to stop it from just looping on itself. The null state is not special as such. I mean, it's not named as such, right? So it would just. We wouldn't necessarily. I mean, the simplest conversion of DFA to PDA is to just give it all the transitions. Right? We could simplify it down and still get an equivalent. Well, we could leave off, I suppose, this part, but that would work, right? And there's no transition out. But if you were just doing a straight DFA to PDA without having to try and figure out whether, is that a null state or, yeah, right? A null state is a null state is a null state. You could have your actual equivalent of null states actually making a kind of a long loop, right? I mean, and you wouldn't necessarily recognize it. So if you wanted a straightforward algorithm, copy exactly the DFA and add empty, arrow empty for each of the stack operations. Right, so that gets us there. But now the $1 million question is, what about those CFGs? You don't want to leave that up there. How about, okay, so can we use this PDA to accept a regular language? Sure, if I got the DFA, regular expression, I can just build it out, right? So now, what about can I use a CFG Well, the problem with things like that example we have where we push stuff on the stack, pop stuff on the stack, is it kind of, and if you look at the other examples, such as page, and that was off of 115 with a couple of variations on it. 116 is the one where it was like the union I equals J or I equals K. We spent a little bit of time on that last time on page 116. And you can kind of see it's pretty clever when you look at it, but how would you come up with that necessarily? I mean, it's not, it may not be immediately obvious. It's going to take some work to get from that state diagram, or from that language definition, A to the I, B to the J, C to the K, I, J, K, greater than or equal to 0, and I equal J or I equal K, right? So you're going to have to do some thinking on that. to come up with a PDA for it. Similarly, the WWR we talked about last time is the string followed by its reverse. And we said basically it's the non-deterministic feature of the PDA that lets you figure out when do I start counting down the other way. Right, so we had pushing zeros and ones on there and matching them at the right point, at the non-deterministic point. We decided to start popping them back off to match up with the rest of the string.
So not always.
So, well, it'll try every possibility, right? It'll try pushing until it finds the end of the string and go, oops, I ran out of characters. And it'll go back and try pushing everything, say, but the last character, and then try popping it off, you know, however you want to picture it, but it'll eventually find the right path if there exists one. So it would be nicer if we had a way to take a CFG and just make it directly into a PDA, or make a PDA that will recognize that CFG. Is there a way to do that? Well, your book does not mention it. Somebody's got to do it.
Are you the man?
I'm the man.
Are you man enough like that?
Well, let's just see. Okay, well, here's what we're going to do. We're going to start with because it is non-deterministic, we're going to make a generic PDA that looks a lot like this, but even a bit simplified. It turns out we can, I'll give you the CFG after. Here's what our template or our basic PDA has to look like. We got start state. And we're going to just do an epsilon and push our $sign on so we can recognize the bottom of the stack. And we're going to get back out of that. Like so. Okay. So now what we need is transitions for Q1. So what would be nice is there some way that we can convert a CFG into a set of rules on that Q1 so that I can just mechanically take the CFG. Here's my little generic PDA, and I can just plug in transitions on Q1 that will recognize the language of the CFG. That sounds pretty cool. It sounds pretty easy, right? Compared to this. What if I could just come up with what is I guess the first place to start, we made one of these CFGs. Remember what the CFG looked like for A to the N, B to the N? It could be as simple as if we requiring n greater than 0, we could do something like that. Right, so there's a CFG, and this is the CFG that will accept, or will generate, I guess we use the term, the CFG generates strings in that language. So all you can ever get out of that CFG, it has two rules, notice, it has S goes to A, big S, B, or it just goes straight to A, B. That includes. So the shortest string you can get is AB, and then any number of A's followed by the same number of B's. Okay. So what we want to do, let's think about what that original examples PDA does. It's using the stack to make decisions about what we're going to where we're going to go from here. All right, so it's keeping track of what it's seen so far. What's the just to give you the motivation, the goal. Come on. Let's say guaranteed. Make a G instead of a Q. Right, so the goal is an easy way to make a guaranteed PDA directly that will just work. I don't have to be clever.
Oh, and the way the question is phrased. Yes. I think,
Well, let's say what I'm going to do here, let's see. Yes. What I'm going to modify right here is I'm going to push the $ and the start symbol, or the start non-terminal, such that they'll end up like $ first, the S on top. So we'll assume that the right-hand thing is what ends up, if I push more than one symbol, it puts the rightmost thing on the top of the stack, and the leftmost thing is added first. So what can I do? If I see, so let's have a little rule. If a non-terminal on top, and I want to say POS top of stack, With the non-terminals on top of the stack, I can just push the right-hand side of its rule on there. I'm going to say left at top. That's important because we're going left to right in our input. And if terminal, there's lowercase letters on top of the stack. Matches input. Pop it off. So there's really only two things that we have to do here, and hopefully this is going to be self-evident.
All these truths to be self-evident.
I hold these true, a bunch of truths to be self-evident, but these also, so they're not in the Declaration of Independence. So, I want to make some transitions. I have a non-terminal on top of the stack. So in other words, I can do, I don't care, I'll do an epsilon move. And if I have S on top of the stack, I want to replace it with that on the top. Really? On an epsilon move, if I see an S, alternatively, I'm going to push just the BA on there. Because I don't care, because this will pick the right one at the right time. Now I just need, let's see, is this better than this? Oh, it is. All done. Now comes the convincing part. Well, how in the world would this work? Can we trace it with, so what we would contend here is that this CFG is the same as this language definition. In other words, that CFG would generate exactly the same set of strings that I would get by applying this notation. Okay? So, what have I done? I've applied the rules. I've made the rules into transitions that can use the stack over here. So let's see what it does. Let's give it our old friend the hey. Oh, which one is good? I'm going to lay the other one down. There's my input. All right, how is this going to work? I turn on the machine. It immediately pushes $, and my chosen start symbol, which happens to be S. Usually we'll use S just generically. And that's what we have to start with. And I'm in Q1, and I have, this is my input, and I'm looking at first A. What will happen? Well, you might try, hey, I'm seeing an A. Is there an A on top of the stack? No. Is there, I'm not looking at a B, so I can't do that one. Well, wait a minute. On an empty move without using any input, I can replace my S with B at the bottom, S in the middle, A on top. Oh, so just take this S off and replace with lightly managed. Okay. I'm still in Q1. So I just took, first option was I applied that transition. And remember, back to that magical non-determinism, it'll try every possible way, and if there exists a way to get to the right place, to the end, to the accept, it will get there. So now, what would I do? Do I have any other transition that I might apply? Oh, I'm looking at an A. Oh, there's an A on top of the stack. Huh. Let's do it. Taking the transition advances the input. And I've got this. Huh. I'm looking at an A, but there's not an A on top of the stack. There's an S. No B in the input. Wait a minute. Can I do this? Sure. I'm going to replace this S with B, S, and an A. Are you with me? I see some nodding. I see a little bit of surprise. Okay. All right. I just did a transition on an epsilon move. Well, wait a minute. I've got an A in my input. I've got an A on top of the stack. Let's do it. Let's take that transition. We'll advance. We'll pop that off. And we are ready for another iteration. Now, my non-omniscient poor little PDA here can't take an A move because there's not an A on top of the stack, but it could do this again, in which case it would replace like that. And eventually it will get into a loop where it will just keep doing that. Well, actually, no, the next thing that would happen, it would match the A to this A, and then it would run into a B. And so it would find that it actually has a B and an S here, and the only moves forward will add more A's on top. So the smart little move, instead of taking this one, well, it would try that one, but then it would more happily try this one, where it would push, this was the BSA. Instead, it would just push the BA onto the stack. How does it do that? Non-deterministically, it'll just try every possibility, right? So one of the right path, right, is this. We match the A to the A, meaning we take that, advance the input, pop that off the stack, and whoa, happy days are here. I've got a B, there's a B on top of the stack, erase it, advance. Whoa, I can do it again. B, advance. It matches again. B. Advance, so we get to the end of the input. And I've got epsilon move. Don't need any input. I used up the input. I got $, pop it off. Jump to Q2. Star. We accept the string. Why this madness? Well, it just gave us a really direct way to take any CFG and turn it into a functional push-down automaton. Right? So what are the two rules that in order to make this work? We supply an epsilon rule that pushes if the symbol we have here, and we'll do next time, we'll do one with other non-terminals, right? This is just the base case, but we do exactly the same thing. Every non-terminal, we make an epsilon move that replaces that non-terminal, the variable, the capital letter, with by pushing its rule on. And the only tricky thing that keep track of is the rule. The leftmost thing has to go to the top of the stack because that's where we're going to be comparing to the next leftmost character. So you have to kind of think of tipping it up so that A is on top. So you have to write the rule to match what the PDA expects. And you just do that for each of for every non-terminal, make a rule that looks like that with its right-hand side being pushed onto the stack. And for every terminal, make a matching rule transition that says, if I see that alphabet character and it is on top of the stack, we match and just pop it off and advance. So this is actually pretty cool. Now, instead of being clever to figure out, let's see, I push some of the stuff on the stack or pop it off the stack, you don't have to figure that out. We'll look at if we can make a, if you can make a CFG for it, we can plug it in to this formulaic PDA and have a recognizer, a PDA that will recognize the same language as your CFG. Just that easy. All right, so you will be responsible for this. We'll talk about it some more next time. It'll be on the review sheet. It is not in the book in this form at all. So let's get it from here. Watching this recording over and over and over and over, that kind of thing. And we'll see you Monday.